Hi everyone, today we will be looking at potential difference and resistance. Alright, so I will start by explaining all the relevant concepts and then going over some practice questions at the end. The learning objectives for this video will be to know what is meant by the potential difference, know what resistance is and what its units are, understand Ohm's law and be able to represent it on a graph, be able to perform Ohm's law calculations using the formula linking potential difference, current and resistance, determine the relationship between resistance and the length of wire, and know what happens to the current and the resistance when you reverse the potential difference across a resistor. So let's make a start. Let's begin by looking at potential difference. The potential difference is defined as the energy transferred per unit charge. So this can be seen by looking at the main formula here. Potential difference equals energy transferred over charge. So this formula perfectly represents this definition. The electric charge is measured in coulombs. Its unit symbol is C and its equation symbol is Q. The potential difference is measured in volts. Its unit symbol is V and its equation symbol is also V. And the energy transferred is measured in joules. Its unit symbol is J and its equation symbol is E. Potential difference is measured using a voltmeter, and this is the component symbol for a voltmeter as we saw in the previous video. Electrons are constantly resupplied with energy whenever they re-enter the cell or battery. So energy is transferred from the chemical energy stores of the cell or battery to the electrical energy stores, which is carried by the current. Electrons use this energy to carry a current around the circuit. The current is the rate of flow of charge, and since electrons have a property known as a negative charge, current refers to the number of electrons passing a fixed point per second. I would recommend watching the previous video on this series if this doesn't sound familiar. Potential difference is referring to the energy transferred by the electrons to each component in the circuit per coulomb of charge that passes through. And this is the energy they obtained from the cell or battery. So when the electrons re-enter the cell or battery, the energy they obtain from the cell or battery is the energy they transfer to all the other components in the circuit. Energy must be transferred to the components to make the circuit function, and the energy is transferred from the electrical energy stores to whatever the relevant energy store of the particular component. So if an indicator is present, the energy will be transferred from the electrical energy stores to the light energy stores of the indicator, and if a resistor or a heater is present, the electrical energy stores will be transferred to the thermal energy stores. This main formula can be mathematically rearranged to obtain two additional formulas as can be seen here. So formula 1 is the main formula we have above. It's the same as the main formula. Formula 2 allows us to calculate the energy transferred given the potential difference and the charge. And formula 3 allows us to calculate the charge given the energy transferred and the potential difference. Now let's look at resistance. The resistance is defined as the opposition to the flow of current around the circuit. The opposition that arises is due to the vibrating metal ions in the wire and in all electrical components. These ions vibrate in their fixed positions and oppose the flow of electrons. So here's the component symbol for a resistor. A resistor is an electrical component used solely for limiting the current in the circuit. The unit of resistance is the ohm, and the unit symbol is denoted using the Greek letter omega. Since resistance is the opposition to the flow of electrons, the greater the resistance, the lower the current, and the lower the resistance, the greater the current. V equals IR is the main formula for a rule we will look at in a moment called Ohm's law. Current is measured in amperes, the unit symbol for amperes is A, and the equation symbol for current is I. The potential difference is measured in volts, the unit symbol for volts is V, and the equation symbol for potential difference is also V. And the resistance is measured in ohms, the unit symbol for ohms is omega, and the equation symbol for resistance is R. So just like before, the main formula can be mathematically rearranged to obtain two additional formulas as can be seen here. So formula 1 is the same as the main formula we have above, but formula 2 allows us to calculate the current given the potential difference and the resistance, and formula 3 allows us to calculate the resistance given the potential difference and the current. Now let's look at resistance in a wire. Electrons transfer energy to other components because of resistance. As we said before, the presence of metal ions in wires and components is the reason there is resistance. An example of this can be seen when electrons collide with the metal ions in the wire. These collisions cause a transfer of energy from the electrical energy stores carried by the electrons to the thermal energy stores of the wire. So the resistance tells us the potential difference needed to drive a current through a component. The greater the resistance, the greater the potential difference needed to drive a current through a component, and the lower the resistance, the lower the potential difference needed to transfer a current through a component. This diagram here shows how resistance works in part of a wire. As you can see here, electrons collide with the positive metal ions. These white lines show the positive metal ions vibrating in their fixed positions. Millions of electrons collide with the positive ions each second when a current is connected to a battery or cell. Now let's look at Ohm's law. Ohm's law states that the current through a resistor is directly proportional to the potential difference across the resistor, provided the temperature of the resistor remains constant. This can be seen in the equation V equals IR, because the greater the current, the greater the potential difference, which implies a relationship of direct proportion between the potential difference and the current. In other words, the greater the current, the greater the potential difference, and the lower the current, the lower the potential difference. The graph opposite shows the current and potential difference of a resistor obeying Ohm's law. A wire is called an ohmic conductor because its resistance stays constant as the current changes, provided its temperature stays constant. So a wire therefore obeys Ohm's law. Reversing the potential difference also reverses the current and makes no difference to the resistance, i.e. the resistance is the same whatever the direction of the current, as can be seen in the graph. This is because since the gradient of the line in the graph depends on the resistance of the resistor, and the way it depends on the resistance is the gradient of this graph here is equal to the reciprocal of the resistance, because R equals V over I, and the gradient of this graph is equal to I over V, because the current represents the y-axis and the potential difference represents the x-axis. To find the gradient of any line, you need to divide the difference between two y coordinates by the difference between corresponding x coordinates. You can see the gradient of the graph is the same in both the forward and in the reverse directions. So since the reciprocal of the resistance is the same in both the forward and the backward direction, or in both the positive and the negative directions, then the resistance must also be the same in the positive and in the negative directions. The greater the resistance of the resistor, the less steep this line will be. And again, this is because the gradient of this graph is equal to the reciprocal of the resistance. And so the lower the value of this gradient, I over V, the greater the resistance, which is its reciprocal, V over I. Now let's look at an experiment in order to determine how the resistance of a wire varies with length. So this is the circuit diagram we will be looking at for this experiment. To measure the resistance of a wire with different lengths, connect a battery to a switch and a variable resistor and an ammeter as shown in the circuit. So the battery is connected to a variable resistor, a switch, and an ammeter. Then connect the wire in question to the circuit. This is the wire we'll be testing. Then connect a voltmeter parallel to the wire in question as shown opposite. So here we have the voltmeter connected parallel to the wire being tested. Then you measure the length of this wire using a meter ruler. Then you record the current and the potential difference across the wire in question at that length of wire being used using the ammeter and the voltmeter. Now change the length of the wire by 10 centimeters and do this by adjusting the crocodile clips in line with the ruler. So to make sure you don't go over or below 10 centimeters. Record the current and the potential difference again. Repeat the experiment 10 times, so each time change the length of the wire by 10 centimeters and record the values for the potential difference and the current using the voltmeter and the ammeter each time you do this. But along with the potential difference and the current, you also need to record the length of the wire used. We can now use the experiment results for the potential difference and the current to find the resistance of each reading by dividing the potential difference by the current. So for example, for the first reading here, we have 0.5 divided by 0.05, and that gives us 10 ohms. So 0.5 volts divided by 0.05 amps gives us 10 ohms. Another example is 2.5 volts divided by around 0.083 amps, and that gives us 30.1 ohms. And here we have the length of wire used for each value of the resistance we have calculated. Then we can use these results to plot a graph of resistance against the length of the wire. The results of the experiment show that the longer the length of the wire, the greater the resistance, because the graph shows that as the length of the wire increases, so too does the resistance. To ensure results like these are obtained, the heating effect caused by the resistance must be reduced. Here are measures that can be taken to reduce the heating effect, since the heating effect can interfere with the results by increasing the resistance, as Ohm's law states. So if we have very large and sudden increases in the resistance, there will also be an increase in temperature. And Ohm's law states that for the current and the potential difference to be directly proportional, the temperature has to remain constant. So in other words, we need to prevent the heating effect. And one way we can do this is to use a cell or battery with a slightly lower potential difference. Another way is to only turn on the current when needing to record a result. In other words, only connect the battery to the circuit when you need to record a reading. Okay, so now let's look at some practice questions. So for each of these practice questions, I would like you to pause the video after I read out the question and try the questions yourself before resuming the video and checking your answers. Okay, question 1 says the current through a wire is 0.5 amps. When the potential difference across it is 4 volts, calculate the current of the wire. So the first thing we need to do is write down the formula V equals IR, because we've been given the potential difference, the current, and we need to find the resistance. So V equals, but the question wants us to find the resistance, so we need to rearrange this equation first before we can answer this question. So we divide both sides by I, and we get V over I equals R, or R equals V over I. So now we substitute 4 volts and 0.5 amps into this equation here. So we get R equals 4 volts divided by 0.5 amps, and the answer to this is 8 ohms. So 8 ohms is the final answer to question 1. So now question 2 says the energy transferred to a bulb is 320 joules when 64 coulombs of charge passes through it. And the question wants us to calculate the potential difference across the bulb. So we have been given the energy transferred, the charge, and we are required to calculate the potential difference. So in that case, we need to use the equation V equals E over Q, or potential difference equals energy transferred over charge. So the first thing we do is we write V equals E over Q. We don't need to rearrange this equation algebraically because it's already given to us in terms of V. So all we do now is substitute the energy transferred and the charge into this equation. So we get V equals 320 joules, all divided by 64 coulombs. And the answer to this is 5 volts. And this is the final answer to question 2. Question 3 part A says calculate the potential difference across a resistor that has a current of 0.45 amps passing through a resistor with a resistance of 22 ohms. So this time we're given the current, the resistance, and we have been told to calculate the potential difference. So we need to use V equals IR, or potential difference equals current times resistance. So we write V equals IR. Now since we have been told to find the potential difference, we don't need to rearrange this equation, so we can just leave it as it is. All we need to do is substitute 0.45 amps and 22 ohms into this equation here. So we get V equals 0.45 amps times 22 ohms, and the answer to this is 9.9 volts. And this is the final answer to question 3 part A. So now for part B, the question says calculate the current across the resistor when a potential difference of 5 volts passes through the resistor. So this time a potential difference of 5 volts instead of 9.9 volts passes through the resistor. And the question wants us to calculate the current this time. So in order to answer this question, we need to use 5 volts as the potential difference, but reuse the 22 ohms from the previous question because the resistance of the resistor hasn't changed. However, this time we need to rearrange the equation to get it in terms of I because it's the current we have been asked to find. So we divide both sides by R so that we isolate the I, and this gives us I equals V over R. So now we substitute the 5 volts and the 22 ohms, and the answer to this is 0.23 amps, but to 2 significant figures. So 0.23 on its own isn't the actual answer to this question. The answer is 0.23 amps to 2 significant figures. So we've used a type of rounding here. If you're not familiar with this, don't worry. I will be posting videos on how to round to however many decimal places or significant figures in the future. But for now, the final answer is 0.23 amps to 2 significant figures. So this is the final answer to question 3 part B. Question 4 here says explain the relationship between the length of the wire used and the resistance. So again, I'd like you to pause the video and have a go on this question yourself first. So we identified the relationship in the experiment we looked at in the slides, and we came to the conclusion that increasing the length of the wire increases its resistance. So the greater the length of the wire, the greater its resistance, and this can be seen when we look at the graph of resistance against the length of the wire. When the length of the wire increases, the resistance also increases, and so that tells us the resistance increases as the length of the wire increases. So here's the final answer. The greater the length of the wire, the greater its resistance. This conclusion can be seen by performing the experiment we looked at before. The greater the length of the wire, the greater the values recorded for the potential difference and the current, but the potential difference increased more than the current each time the length of the wire was adjusted to be longer. So after calculating the resistance for each pair of current and potential difference readings, then plotting a graph of resistance against the length of the wire, it is clear that the greater the length of the wire, the greater the resistance, or in other words, the resistance was increasing because the potential difference needed to push the current around the circuit was also increasing. So if you got at least 4 points I mentioned here, then that's great. Keep up the good work. And hopefully you did just as well in all the other practice questions we looked at. So this brings us to the end of the video. I hope that you found this video useful and that you understood the concepts of potential difference, resistance, and Ohm's law. If you have any questions, please post them in the comments. I would be more than happy to help. You can also attempt more questions down in the video description. If you find these videos useful, don't forget to subscribe and share the video. More videos like this are coming soon, so do keep an eye out. Thank you for watching and see you all next time. Goodbye.